Ionisation enthalpy is one of those topics that sounds tricky, but once you crack the key patterns and exceptions, it makes so much sense. In this video, I'm going to take you through what ionisation enthalpy actually is, why it's useful, and how to predict trends across periods and down groups in the periodic table. We'll look at why some elements don't quite follow the trend you'd expect, and the classic exam traps you need to watch out for. So if you're studying A-level chemistry and want to feel more solid on this, you're in exactly the right place. Let's dive in. And if you find this helpful, don't forget to hit subscribe for more A-level chemistry walkthroughs like this. Okay, so ionisation enthalpies. First of all, what are they? Ionisation enthalpies provide the evidence for how electrons are arranged, otherwise known as electron configuration. That is the whole 1s2, 2s2 thing. And if that is confusing to you, then go back and check the previous video on my channel because it's all there explained for you. Okay? Now, an ionisation enthalpy is sometimes known as an ionisation energy, depending also at what point in your A-level you are. So at AS, you can get away with saying ionisation energy. When it gets to A2, then you'll need to start saying ionisation enthalpy. What is it? Well, first ionisation enthalpy is the enthalpy change to remove one electron from each atom in a mole of atoms in order to create 1+ ions all in the gaseous state as a gas. I've simplified that here and called it removes the first electron. That's your understanding. The full definition is the bit that I just gave you, but what it means is it's removing one electron. I've shown you an example there of an equation. So for instance, the first ionisation enthalpy takes sodium as an atom in the gas state, removes one electron to produce a sodium 1+ ion, again in the gas state. And the electron that's lost is shown on that right-hand side of the equation as +E-, meaning one sodium atom goes to make one sodium ion and one electron that has been lost. Now, the second ionisation enthalpy, and we can go third, fourth, fifth, etc. We'll talk about that more a little bit later when we talk about successive ionisation enthalpies. But the second ionisation enthalpy for anything takes you from a 1+ ion to a 2+ ion. So it's creating or it's removing the next electron. Okay, so that's what they are. Now let's think about what might affect the energy required to remove an outer electron. So these are the three key factors to explain the size of the ionisation enthalpy, the energy required to remove an electron. The first one is size of the atom, meaning the bigger the atom, then the nucleus with the positive charge in from the protons is further away from the outer electron that is being removed. Therefore, there is a weaker attraction between that nucleus and outer shell electron, and therefore requires less energy to remove it. So the ionisation enthalpy is smaller. Conversely, if we have a smaller atom, you have a stronger attraction between the nucleus and the outer shell electron, and therefore more energy is required to remove that electron. The second factor is the number of protons. So the number of protons that is in the nucleus, so the positive charge of the protons is in the nucleus. If you have more protons, then you have a stronger attraction between the nucleus and the outer shell electron. And that therefore makes the ionisation enthalpy higher. Conversely, fewer protons, weaker attraction between the nucleus and the outer shell electron. So therefore, less energy is required to remove the outer shell electron. And the final one there is shielding. So shielding refers to the repulsion by the inner shells of electrons. Now, I use a really bad analogy here. So if it contributes towards your understanding, take it. If it doesn't, leave it. Imagine you are attracted to another human, okay? You fancy them. Imagine that you are in a hall and at the moment the hall is empty. There is nothing between you and that person you are attracted to. So therefore the attraction is strong. You can see them clearly. We're drawn together. However, imagine now that you're in that hall, but it's full of lots and lots of other people. So the attraction between you and that other person is less strong because there's more people in the way. And it's a little bit like that for shielding. Electrons are negative, so they are always repelling each other. So if you have more inner shells of electrons, you have more electron-electron repulsion happening, meaning the attraction between the nucleus and the outer shell electron is therefore weaker. So more shielding means that you have a weaker attraction between the nucleus and the outer shell electron, and therefore the ionization enthalpy is lower. Conversely, if you have less shielding, stronger attraction between the nucleus and the outer shell electron, and therefore the ionization enthalpy is higher. Let's now use these three factors to explain trends in the periodic table. Now, this first trend is down a group. I'm using, for example, here group 2, but the same logic is going to apply to any group in the periodic table. So you can see there that the trend is that as you go down the group, the ionization enthalpy is decreasing, it's getting smaller. Let's use our three factors to explain why. So the first factor was size of the atom. Now, as you go down the group, the atoms are getting bigger because you have an extra shell of electrons. Because you have this extra shell of electrons as you go down the group, you also have more shielding. That means overall, atoms are bigger, more shielding. There is a weaker attraction between the nucleus and the outer shell electron. That explains why less energy is required to remove an electron. Now you might be thinking, hang on, what about that third factor, the number of protons? Good point. Okay, as you go down the group, we do get more protons. But that does not explain this trend. Like if we do this and we measure it, the trend does decrease down the group. If it was the number of protons that was explaining this trend, we'd expect to see that ionization enthalpy increasing, but it's not. So it must be these other two factors of atoms getting bigger, more shielding, that has a much bigger effect, bigger impact on the attraction between the nucleus and the outer shell electron. Okay, let's look at the next trend now. Now let's consider the trends across a period. Now a period in the periodic table is the rows. Okay, the first period is hydrogen and helium, and then second, third. Now I'm using, for example, here period 3, which you can see here starts with sodium and ends in argon. But the same thing is going to apply to any single period on the periodic table. Now we're first of all going to consider the general trend, and then we're going to look at those two exceptions where the line goes a little bit wiggly. So the general trend there, you can see that the ionization enthalpies increase across the period. Let's consider our three factors. Size of atom was our first one. Now across a period, the atoms get smaller. Why? Great question. Because as you go across the period, the number of protons is increasing, and therefore there is a stronger attraction for the electrons, which is therefore decreasing the atomic radius. So there's our first factor that affects the energy required to remove an electron. The atoms are getting smaller, i.e. therefore argon is the smallest in that period. The second factor is that we have more protons. So as you go across that period, each element has one more proton. And therefore, overall, that means we have a stronger attraction between the nucleus and the outer shell electron to be removed. Your third factor, shielding, that doesn't change across a period because all of these additional electrons are all in the same shell in a period. So the atoms are getting smaller, we have more protons, but the same shielding. And that's therefore why you need more energy to remove that outer shell electron. There are a couple of key exceptions that you can see there though. So this first exception to this general overall increase is the group 2 to 3 dip. Now when we're talking about period 3, that is magnesium to aluminium. But again, remember, the same logic applies to any period in the periodic table. So it's any group 2 to 3 dip, you will see the same book in the trend. Now it can be explained when we consider where the electrons are in the electron configuration. So if we think about magnesium's electron configuration, magnesium's electron configuration is 1s2, 2s2, 2p6, 3s2. So the highest energy electron is in that 3s orbital. However, if you look at aluminium, which is the next element on, so it has one more proton and one more electron, its electron structure is 1s2, 2s2, 2p6, 3s2, 3p1. So the electron being removed is from a 3p orbital. Now that's important. The electron being removed is from a p orbital rather than an s orbital. And p is higher in energy than s, which means that it requires less energy to remove. Now that can be confusing, so I often give the analogy of a well. So imagine for me a well, a big hole in the ground that fills up with water, okay? If you have less water in the well, a lower energy electron, in order to get some water out of the well, you take your bucket, you lower it down into the hole, and then it has to go all the way down, and then you have to use your energy to pull it back out. It requires more energy to get the water out of the well when the water level is lower. And it's kind of the same thing happening here. The lower energy that the electrons have, the more energy is required to remove them. So the key points there that I've given you, that's the way to structure it in an exam. Point out where the electrons are from. The electron being removed in magnesium is from a 3s orbital. The electron being removed from aluminium is from a 3p orbital. P electrons are higher in energy than s. Full stop, 3 marks, full marks, we're good. Okay? The next dip happens between group 5 to 6. So if we're looking at period 3 specifically, that is phosphorus to sulfur, P to S. Okay, now it's a completely different reason why we see the ionization enthalpy dip here. But again, we can explain it using electron configurations. So let's look at the electron configuration for phosphorus first. So phosphorus, the full electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. And if we look at that 3p3, you can see there in the diagram that each electron fills up in one orbital. So they're all in separate orbitals. And that can be explained by Hund's rule, meaning electrons repel each other. It is more stable to reduce electron-electron repulsion. So therefore, separate orbitals reduces how much those electrons repel each other. And that's why you see them separate like that. However, when you consider sulfur's electron configuration, then it is 3p4. So you have one electron in each orbital, and then the fourth electron has to go back and pair up within an orbital. And that means there's more electron-electron repulsion in sulfur, meaning less energy is required to remove that electron. Now, a key word there when you are explaining it is the word more. Electrons repel each other anyway. So in phosphorus, those 3 electrons in 3p, they are going to be repelling each other because they are negative electrons. However, in sulfur, when the electrons are paired up, then the electrons are repelling each other more. So keyword there is more electron-electron repulsion in sulfur, and that's why less energy is required to remove that outer shell electron. Successive ionization enthalpies refers to the idea that we're removing one electron at a time. So we do the first ionization enthalpy, then the second ionization enthalpy, and then we remove the third electron, the third ionization enthalpy. And we do that all the way through until there are no electrons left. Okay. Now, first of all, those trend upwards, i.e. it requires more energy to remove each electron as you go. And that's because you're removing an electron from an increasingly positive ion. So successive ionization enthalpies always increase because the ion that you are removing that electron from gets more and more positive. Now, the reason why this is useful is because it's providing evidence for electrons being in shells. Now, this example I have here is of potassium. So you can see there that potassium, you remove one electron and it's in group 1, so it has one outer shell electron first. That's the lowest ionization enthalpy. Then we have a really big jump. And the next electron, the second electron, requires much more energy to remove. Now that tells us which group it's in, because if it is one electron that is in the outer shell, the next electron in the next closest shell has a greater attraction to it because it's much closer to the nucleus. So that big jump tells us in this case that this is a group 1 element. If you removed 2 electrons and then you had a big jump, that would be a group 2 element. The third electron is the one that's much closest to the nucleus and requires much more energy to overcome, and so on and so forth. If you removed 3 electrons and then a big jump, then that is group 3. If for some reason you see no big jump, then it would be a group 0 element. It's also interesting to see here. So if you can see for potassium, we have 1 electron, and then we have 8 in the next batch. And then in the next batch, another 8, and the next batch, the 2. So that again is the evidence for these shells. We have 2 right closest to the nucleus, then 8 in the second shell, then 8 in the third shell, and then 1 in the fourth shell. So time to sum up. What have we learned in this session together? We've looked at the idea that ionization enthalpies provide evidence for how electrons are arranged. They're arranged in shells. We've looked at that there are 3 factors mainly affecting the ionization enthalpy. Size of atom. The bigger the atom, the greater the ionization enthalpy. The number of protons. The more protons, the more positive charge we have, the stronger attraction between the nucleus and outer shell electron. Again, a bigger ionization enthalpy. And if you have more shielding, more repulsion between those inner shells of electrons, then that therefore decreases the ionization enthalpy. We've also looked at how higher energy electrons require less energy to remove. And we looked at that when we were explaining, for example, the 2 to 3 dip across a period. It bucks the trend. Using those 3 factors, we can also explain the trends in ionization enthalpy down a group and across a period, and the group 5 to 6 dip. And then finally, we looked at how successive ionization enthalpies can show us which group an element is in. Now, if this was useful, then please join me for the next video and I can help you out all the way through your A-level chemistry. Share with a friend and hit subscribe now. Thank you again for joining me for today's lesson. And if you haven't already, hit subscribe so that we can continue learning together, and perhaps share this with someone else who also wants to understand chemistry.